Okay, so let's start. So I chose some problems from old exams, but they are very important. They have very important. They have very important idea. Let's start with this one. So figure 1 shows a snapshot graph of a wave traveling to the right along the string. So first of all, the wave is traveling to the right. Oh, sorry, one moment. So it is traveling to the right along a string at 25 meters per second. So this one, we start by writing v is equal to 25 meters per second. At this instant, what are the velocities of point 1, 2, 3? So the points are here, 1, 2, and 3. So there's points on the string respectively. Okay, great. First of all, we need to look at the graph. We need to look at what are we plotting. So here we are plotting the displacement d as function of the position. So be careful. Whenever you have a wave, you can have a graph of the displacement as a function of the time or the position. So you need to identify that at the starting. So here, as a function of x, which means at a given time, we take a snapshot. We take a snapshot of the wave. Okay, here they require the velocities 1, 2, 3 for these points. To get the velocity of these points here, we need to think this way. We have a wave traveling to the left. So this is at instant t or t0. At an instant t0 plus dt, so after small time, this wave, since it is traveling to the right, it will be something like this. I will try to plot it this way. Up. So there is just a shift. It's a shift in the wave. We have a shift in the wave. So after a small time, the wave will look like this red curve here. The second information that you need to know is that a point in the medium where the wave is propagating does not propagate. It oscillates in the same place. What does it mean? A point does not propagate, but it oscillates in this direction, in the y direction. So it oscillates at the same position x. So this one, it was here, and then up, it will go down like this. This one, it was here, and it will go up. This one, it was here, and of course, since it is maximum, it will go down like this. So here we can see the different velocities. So we know that 1 is negative, 2 is negative, and 3 is positive. For 2 here, actually we do not know if it is negative or positive because actually it is 0. And we can deduce that because it's a maximum. When we are at the maximum, the velocity will be 0. So you see here, it's very, very small. It's starting to become negative. So this one is 0 because we are at the maximum. We have 1 is negative. This one is positive. If I look at the choices here, negative, 0, positive. I have this one, negative, 0, negative. So this one, no. This one, no, because we know that the velocities here are maximum. This one, no. This one also is possible. So I need to choose between the two here, negative, 0, positive. So this information, we got them from the graph. We need to do some math now. So we know that U max is equal to omega ym. And of course, this is in absolute value. Omega m. So this one is the transverse velocity. The transverse velocity. Here we are calculating the transverse velocities. And we need some information. Omega is 2 pi f multiplied by omega m. And the frequency, we can obtain it from the graph because it's v over lambda. And from the graph, you can see here from the valley to the valley, this one is 30 centimeters. This one is lambda. So we can put here also an information, lambda is equal to 0.3 meter. I need to be careful about the units. This one in centimeter, so I need to put it in meter. So it is 0.3 meter. So if we come back to our relation here, we can calculate. It's given, V is given 25 meters per second. Lambda is 0.3, and this will give me a velocity, a frequency of 83.33 hertz. Okay, so we have F. Since we have F, we come back to this relation here, and we get U max is 2 pi multiplied by 83.33 multiplied by Ym. Ym, we read it from here. It's the maximum displacement. It is 2. And the unit, I need to be careful, 2 centimeters. So 10 minus 2. By doing the math here, I need to get 10.47, which is closely meter per second, 11 meter per second. Okay, so I know here at this point, I have a maximum velocity, which is U max. And this one, at the maximum point, I have a 0 velocity. So I got 11 up, and the signs are correct. The signs as I deduced them from here. Great. So here, the message that I want you to keep in mind is that you can after some time, after small time, the wave shifts to the direction of the velocity here. The second remark is that any point in the rope or in the medium does not propagate. It oscillates at the same place. It oscillates at the same place. From that, you can deduce the sign of the velocity. Is it positive or negative? And just a warning: be careful about the units. You need always to know what is plotted here in the graph as a function of what, and you need to be careful about the units. Okay, so this is the first problem. Let's go to the second one. Let me check if I have here some message in the chat room. Okay, no question in the chat room. Question or midterm number 2 here. Okay. In the second problem, we have a string of 80 centimeter length. So we have a string of 80 centimeter length. It is fixed at both ends. So we have an end here, another end here. The string oscillates in the fundamental mode with a frequency of 60 Hertz and the maximum amplitude of 0.20 centimeter of the standing wave. So here it is something like this. The fundamental is something like this. So we have, it oscillates between these positions here. So this is the fundamental. We have the length, we have the frequency of oscillation, and we have the maximum amplitude also of the standing wave. What is the maximum transverse speed of a particle oscillating in the string at x equal to 20 centimeters? At x equal to 20 centimeters. So we have here a point at 20 centimeters, let's say this one here. We want to know what is the maximum transverse speed. What is the maximum transverse speed? Okay, so to answer this question, first of all, I need to know what is the relation between the new displacement, we call it y prime, x and t, as function of omega and t. So we have this relation. Ym is equal to 2ym sine kx cosine omega t. This one is the function which is varying in time, and this one will be, the red one will be considered as the amplitude. The absolute value of this will be the amplitude. So this one is a displacement for the standing wave here. If I want the velocity, which is u, I would call it u of t, for example, x and t, of course, it will be the derivative of this one. So I need to derivate this function over time. So dy prime over dt. This will give me 2. The derivative of this one will give me minus, because I have cosine, and it will give me also an omega, which is inside here, and the remaining ym sine x kx. This one does not change. And here the derivative of cosine, we said it's sine omega. So because of the derivative, we got an omega and the minus sign. As you see, this one is varying in time. So all the factor which is here will be our Umax. Because this one, the maximum value of this one is 1, this one gets 1 or minus 1 in absolute value. So all this will be the maximum velocity, transverse velocity. So Umax will be the absolute value of minus 2 omega ym sine kx. So this is Umax. Okay, now from the graph here, what can we deduce? There is a word which is important here. It's the fundamental. The fundamental, we know this shape, and since it is the fundamental, we can deduce that this shape here is lambda over 2. Okay, lambda over 2 is equal to L, of course. The total length is equal to lambda over 2. And from here, we can deduce that lambda is 2L, and it will give us 1.6 meter. So we have lambda. Lambda is 1.6 meter. Omega is equal to 2 pi f. They gave us the frequency of oscillation, which is 60 hertz. So I will use 2 pi multiplied by 60 hertz, and this will give me 120 pi. Of course, this one is radian per second. This is if I want to write the unit. I can let it. I can let pi here or do the numerical application. It's not a problem. I come back here to this relation Umax. So I need 2 omega, which is 120 pi. Ym, they gave us the maximum amplitude here is 0.20. So it's 0.20 or 0.2 multiplied by sine. And k, I did not, they did not give us k, but we know that k is 2 pi over omega. Omega is 2 pi over k. K is equal to 2 pi over omega. So it's 2 pi over 120 pi. This is omega. This is k multiplied by x. So we are looking at the point here at 20 centimeter. So 0.2. I need to be careful about the units. Up. And this at the end will give me 53.3. Of course, here I worked with meter per meter. So this one 10 minus 2 meter per second, and this is equal to 53.3 centimeter per second. I'm working in the international unit. The result will be in the international unit, which is meter per second, and then I can change it to centimeter per second, and this will be the answer. So the velocity of this point, which will be oscillating between this point and this point here, oscillating like this, the maximum velocity will be 53.3 centimeter per second. So you need to keep, yes?
The amplitude is 2 centimeters.
The amplitude here is 0.2, yes.
It's in centimeters.
Yes, no, in meter, 0.2. Oh, centimeter. Probably, I'm sorry. In that case, the result is in centimeter per second. I thought that I had the result in, oh, yes. Sorry about that, yes. So the result, I know that the final result, I did this one up, so it should be the result 53.3 centimeter per second. Yes. So thank you very much. Very important remark. So whatever you put here for y will be the unit here for u max. If you put meter, you will have meter per second. If you put centimeter, you will have centimeter per second. So since this one, I thought it was 0.2 meter. It seems here 0.2 centimeter. So the result will be directly in centimeter per second.
What
Great.
about
Thank you very
the
much.
X vector?
The X inside here, you need to use meter. Be careful. Inside, 0 to 10. Yes, I need just to correct this. One moment. Up. The final result is correct. It's just here, since I want quickly. So 10 minus 2. I need to put it in meter here. I need to put the international unit. So this one, I need to express it in meter inside. And one remark. Be careful about the angle. The angle here should be in radian. So usually in the chapters 16, 17, 18, everything will be in radian. So the angles will be in radian. Most of the time they will be in radian. And here I have a question: why we use the equation of particle in opposite direction? We are using that. We are using this equation because in order to have a standing wave, you need to have in order to have a standing wave between two ends, you need to have an interference between two waves moving in opposite directions. In opposite direction. And why omega over k? This one is a rule. You have it. So the relation between omega and k is this one. Omega is 2 pi over k, or k is 2 pi over omega. So all this relation, all these relations here. Sorry, one moment. Yeah. I'm 2 pi over lambda. Yes, someone of you up 2 pi over lambda. Yes, I'm sorry. I'm going very fast. I need to slow down. 2 pi over lambda, and 2 pi over lambda. So here f. Okay, omega we got it, and k is 2 pi over lambda. So what is lambda is 1.6. Yes. Sorry, I'm going very fast. I need to slow down. So I will summarize here. K is equal to 2 pi over lambda. Okay, and omega is 2 pi. Omega is equal to what?
2 pi f, I think.
2 pi over t. Okay.
And velocity is omega over k.
What? Yes, v is omega over k. This is for v. And here
Can
you
you
see
show the value of x?
2 pi. Here t, 1 over t is f. 1 over t is f. So we have this relation. Okay. What's the other question?
The value of x.
The value of x is given here is 0.20 centimeter. 0.20 centimeter. So 0.2, 10 minus 2 meter. So this is fine. Here I put it in centimeter, no problem. I can put it in centimeter, no problem here. My result will be in centimeter. If I want to put it in meter, my result will be in meter. But inside, I should use meter per second. Inside, I need to use the meter per second. Outside, you can use whatever you want.
It is
And the result
20 centimeter, Doctor.
Oh yes. Yeah, I'm very sorry. Yes, at the beginning I wrote it 0.2, but when I saw this one, I said, "Am I doing a mistake?" It's this one. Yeah, it's this one. Sorry. Yeah, it is. Yeah, I'm confused between the two numbers here. I had in mind that it's 20 centimeter, but then when he showed to me this, I'm confused. It's 0.2. But anyway, it's the most important thing. Of course, you need to concentrate. But Here I'm teaching you the method. I'm more concentrating on the method than on the number. So keep in mind this. Whatever you use here will give you the unit of Umax. Inside, you need to use the international unit because this one at the end should be in radian. So this one should be in meter, and omega here should be radian per second for ohms. Okay, great. Yes, here be careful about here. The system is oscillating in the fundamental. In the fundamental, you can deduce from that lambda over 2 is equal to L. The shape of the fundamental is this one. If it is a second harmonic, you should know what is the shape of the second harmonic. Okay, we are a little bit late. Just 2 minutes, no problem, that's fine. We move on. Yeah. So this problem here, as you'll notice, I'm sure that you have been solving a lot of problems. You may have met this kind of problem. It's about interference. I did a small change in this problem, and I'm sure that many of the students will be confused because of the change. I will show it now. So we have two transmitters and S2. They emit identical sound waves at a frequency of 686 Hertz. The transmitters are separated by a distance of 2 meters. So the distance between S1 and S2 is 2 meters. Consider a big circle of radius R with its center halfway between the two transmitters. So here, the two are symmetric. How many interference maxima are there in this big circle? Okay, you have seen a version of this one where the two are perpendicular like this, one here, one here. Now they are tilted here. The segment S1, S2 is tilted. It has an angle, and they do not give us what is this angle. They do not give us the angle. All what they gave us here is the distance. S1, S2, they say is 2 meters. Okay, S1, S2 is 2 meters. Now, what's the other information that we can have? The lambda. We need to get lambda. In all these problems of interference, most of the time we should get lambda. Lambda, it is V over F. V over F. The velocity is not given here. Since it is not given, we know that it is a sound wave. Is it? Sound waves? Yes, here. Since we are working with sound waves, we need to use the velocity of sound in air. So 343. It is in your formula sheet. So you use this number, and the frequency here 686, and this will give you 0.5 m. 0.5 m. This is important. At the end here, you can notice that S1, S2 is, I need to express it in terms of lambda. In terms of lambda. Since it is 2, you see it's 4 times lambda. 4 times lambda. So this one, you can see directly it is 4 times lambda. You can do the fraction here to know what is the number. Okay. Now, in all problems of interference, we can have this one, we can have a different shape. The most important thing is that you need to express, let's say for a point here, for example, you need to express the difference of length between the two waves. So there is a wave coming from S1, another coming from S2. This one is L2, this one is L1. So you need this delta L. Delta L will be L2 minus L1. And depending on the shape, it can be spherical here, or we are looking to point. We are investigating points on a circle. There can be points on a triangle, whatever. And of course, we start by starting this delta L is equal to L2 minus L1. The distance L2, we do not know that. We do not know L2. We do not know L1. We can probably make some difficult math here between the position of this one. We do the coordinate. We get what is the value here. It's very complicated. The easy way for this one. If I look at this axe, I will plot an axe the axis here, sorry, we plot the axis here like this, passing through the 2. And another axis here perpendicular to it. We have another axis perpendicular here. So here, when I am here at this point, the distance between S1 or S2 to the point P minus S1 to the point P will be this one. It will be this distance. I hope that everyone agrees with that. So S2 P minus S1 P will give me this distance. So when I'm here, I know that the difference between S2 P and S1 P is 4 lambda. So here it is 4 lambda. Okay, the distance is 4 lambda. Here, when I am here at the perpendicular point here, you see I took it perpendicular to S1 and S2, so it is perpendicular. And at the same time, here it's the center, right? So I know that the distance from this point here, P, to S1 and P to S2 is 0. The distance between the difference, delta L, as defined here, will be 0. So the distance here, I can write it 0 lambda. 0 lambda. Okay? The same thing here. If I am at this point, it will be 0 lambda, the distance between this one to this one. And when I am here, the distance between, of course, the distance is in absolute value here. We look at this is in absolute value. So S1, this point, and S2, this point, the distance between them will be S1, S2, and it will be again 4 lambda. It's this one, 4 lambda. Okay, so I started with these characteristic points. Now, what happens when I go from 0, this point P goes this way. I know that when I am here, the distance of S2 P and S1 P will increase. This one will be larger than this one. Okay, great. So the distance will increase until I go or until I arrive to this one, to 4 lambda. So what I can deduce from that, at some moment I will pass here by a point where the difference is lambda. I don't know where is the point exactly. I don't know where is it exactly. But since I'm going from 0 to 4 lambda, for sure I will pass through 1 lambda. I will go, so continue. I will pass through a point which is 2 lambda. I will pass through another point where I will have 3 lambda. Because to arrive from 0 to 4, I need to pass from 1, 2, and 3, and 4. So I have these points. What's the characteristic of these points? They are integer multiplied by lambda. When we have an integer multiplied by lambda, n lambda, if the difference delta L is equal to n lambda, this is constructive. Constructive interference. So here I have all these points. The same thing. If I go this way from 0 to 4 lambda, the distance between a point here to S1 and the point here to S2 will increase from 0 to 4. So I will have here 1 lambda. I will have somewhere 2 lambda. I will have somewhere 3 lambda. I don't know exactly where, but it doesn't matter for me. So I have this point. From 0 to 4 here, I will have 1 lambda, 2 lambda, 3 lambda. And so on. From 0 to 4, I will have somewhere 1 lambda, 2 lambda, and here 3 lambda. If I count everything, I will find 4, 4, 4, and 4, 16. 16 points. So I have 16 points. So the main idea here is you need to express this delta L for some characteristic points, let's say here and here, because here we can do, we can extract it exactly. Here we are sure that it's 0 by symmetry, and here we are sure that it is this distance. So from 0 to 4, I can go from 0, 1, 2, 3, and then I get 4. I do it the same way, and I get all the points. So you see, this happens even if the 2 points here are tilted like this. They did not give us what is this angle, but it does not matter. It does not matter. You need to think this way. You need to express delta L, and you need to express it in terms of lambda. So here, all is expressed as a function of lambda. Imagine they want how many interference, not maxima, but minima. Okay? In that case, I will say I have here 0, I will have 0.5, I will have somewhere here 1.5, I have 3.5, I have here 3.5 somewhere here, and that's it. And then here 4. So I know that when I have this half integer, it will be a minimum. It will be a minimum. So the idea, if they change how many interference minima are there in this big circle, I need to count all these numbers, 0.5, 1.5, 2.5, and 3.5.
Mr. Adel.
And yes, تفضل.
The maximum is are they the notes?
Here, yes, they are the nodes.
So should it be lambda over 2?
No. No. Look, the difference between two waves, it's not the same. It's not the same way. It's not an interference between waves, opposite waves. Be careful. Here we are talking about interference between waves going almost in the same, let's say in the same direction. Okay, so we need to have a difference of phase, which is either 2 pi, or when we discuss lambda, we say n times lambda. In order to be in phase, it should be lambda, 2 lambda, 3 lambda, and so on. So interference should be this way, lambda and multiple of lambda. Very important. If it is destructive, it will be, destructive will be lambda over 2, and you need here 2n plus 1. This one destructive.
So the nodes
are multiple of half lambda.
Here, let's say maxima, not nodes, because nodes it's a term that we use usually for standing waves. Here, it's not a standing wave. Okay, it's not a standing wave.
Okay.
Here you have
equal to
here delta L is equal to n plus 1. It is an even number, an odd number of half integer, an odd number of lambda over 2. Sorry, lambda over 2. Okay, you can check this again in your lecture. Let's move on. So if you have questions, you can ask me later on, of course. Okay, here, number 4. In this one, we have 2 sinusoidal waves, identical. Sorry, someone is talking?
Yes, sir.
Yes?
Please like to the brief. Yes, sir.
I did not.
For 1 second.
Okay, I will give you the answer. I will give you the answer later on. Let's move on. I will give you the answer. You can contact me. I send you the answer. Okay, so here we have 2 sinusoidal waves, identical except for the phase. They travel in the same direction along a string. They are given by y1 by this relation and y2 by this relation. So you see they are identical, moving in the same direction. Here we have minus, here we have minus, and we have here we have a phase, an additional phase, where x and y are in meter and t is in second. At what average rate does the resultant wave transport the energy? Okay, so first of all, we have waves. So they are propagating in the same direction, and there is a phase between them. We know from our lecture, whenever we have that, the 2 waves, we need to sum them like this. We need to sum them, and the result, we can use directly the result. The result is like this. We know the relation. The relation, the resultant wave is like this. It is 2ym cosine phi over 2, and here sine kx minus omega t plus phi over 2. So you see, it is still a propagating wave. It is still a propagating wave. It's not a standing wave. So we cannot talk about a node. That's why previously I said it's not a node. It is a maximum. Okay, great. So we have this. Now they want the energy rate, the average rate, and the average rate, the resultant wave is transporting energy. So it is what we call here P. We define P average. Average like this is equal to 1/2 mu v omega square and I. So this is ym. Of course, this is the rule that you studied for a wave. Okay.
سكوير دكتور.
Yes, yes. I'll write it right now.
يا شباب قطع ولا عندي بس؟
Yeah, so this is what you studied in the lecture. Be careful here. There is a small. They're talking about the resultant wave. They're talking about the resultant wave. So here you need to write y prime. Just to remind you that you need to study this one. Okay? So you need to use the amplitude of the resultant wave, which is not ym. Which is not ym. It is different. So what is here y prime? Just recall y prime. It is all this term here, 2ym cosine phi over 2. Okay, so this is very important. Now, let me first change this one like this. We have the equation here. So the equation, I will write all what I can extract. Ym is equal to 0.025, and they said it is in meter. Okay, great. I have the phase pi. The phase between the two is pi over 3. Of course, it is in radian. I need the phase. Ym is obtained here, so I can calculate this one is 2 multiplied by 0.025 multiplied by cosine pi over 6. Okay, and cosine pi over 6, pi over 3, pi over 6 is 1/2. This one is 1/2, and this one will give you, should give you 0.025. Oh yes, actually, I don't like this number here because pi over 3 will give you 1/2. It will simplify with this, and you get again 0.025. So even if you work with this one, you will obtain the correct result, but it's just a coincidence. It is just a coincidence. So be careful. In general, you need to use this term here, y prime. Here, by coincidence, we obtained the same y prime is equal to y, but it's just a coincidence.
Doctor,
okay. Yes?
What does coincidence mean?
Coincidence, which means here, because pi over 3, they gave you a phase which is pi over 3. If the phase here pi was different, if this one was pi over 6, you will get a different number here, which is different from this one, 0.025.
Doctor,
Sorry?
sorry for interrupting. I calculate the answer. It give me 0.43, not 0.25 in radian.
No, wait, cosine. You have pi over 6. Sorry, square root of.
It is square root of 6.
Yeah. Yes. I like this better. I like this one better. Square root over 3. Square root 3 here. Up. Yes. Can you give me the number? I not have it here, the calculation.
0.0433.
Great.
It's 0.4.
0.4. Yes.
Yes.
So I like this one better because it shows you that y prime is different from ym. Okay, so you need to use this one, of course, because the relation as I wrote it here is y prime. Why I wrote this? Because they want the energy for the resultant wave, not for this one, not for this one, but the resultant wave. Okay, mu is given here. Okay, so v, the velocity v, yes. What we can extract from here, this is k. We have k, which is equal to 15. Okay, radian per meter. What else? We have omega, which is 90 radian per second. Okay, and so we can get the velocity v of the wave is omega over k, which is 90 over 15, and this should give 6, if I'm not mistaken, 6 meters per second. So we have v, we have omega, we have everything. So p average is equal 1/2. Mu is 500 grams per meter. So I will write it 0.5 kilogram per meter. I need to use the international unit. The velocity is 6 meters per second. Omega is 90. We said it's 90. So 90 square. And y prime is given here 0.043. Okay, square. If I do the math, I don't know if I have the result here. Let me see.
22.78.
Yeah, it is
Correct.
It should give this one. Please do the math and tell me if it gives this one. Yeah.
Yes, it gives
So the idea is very
22.78.
important. Okay, yes, great. So it is this one. Great. So be careful. You need to know this rule here. Okay, this formula here. So you see the resultant wave has an amplitude. The total here is the amplitude here. Okay, or the absolute value of the absolute value of this one is the amplitude, because the cosine can be negative. So the absolute value here is amplitude. It can be maximum, and the maximum is 2ym. It can be minimum, and it will be 0. Okay, so this is very important. And still, this one is propagating wave. You can extract all the information from here, and you do the relation here. They told you resultant wave, you need to use the resultant amplitude here. Okay, great. Let me continue.
Doctor,
Yes,
how we get the mu?
mu is given here. Is given.
Oh, okay.
Yeah, mu is given.
Doctor,
If yes,
how about ym displacement?
this. Okay, what was the number? Number 3, I think, right? The displacement is the relation that I showed to you. It's number. Sorry. One moment. Sorry. So the displacement is all this one. 2ym cosine phi over 2. This one is the rule from your lecture.
Doctor?
Yeah. But,
yes.
I have a very shortcut for the previous questions. Can you go back to benefit the student? Very
For
short.
this one?
No. Previous, which is question 3.
Can you let it at the end, please?
Yes. Okay.
I will stay at the end. I will take all the questions.
Yeah, because I will benefit the student. It's very short. Just for looking, you know, which is okay. Take your.
Yeah. Sorry, I'm just a little bit late. So please, I will take the other questions later on, if you allow me. Just bear with me. Yeah, I will stay at the end, and we can answer all the questions. So here in this chapter, it's about what we call Doppler effect. We have a car which is approaching a reflecting wall with a speed v car, here vc. The stationary observer behind the car hears a sound of frequency 828 hertz directly from the car horn, and the sound of frequency 971 hertz reflected from the wall. So we have a sound which comes directly like this from here, and another sound, it comes reflected from the wall. So we have two sounds. Find the speed VC of the car. So they give you the two frequencies that they hear here, and you need to find what is the velocity of the car. Okay, so first of all, we need to write the relation says F prime is equal to F V plus minus V. Here it is detector over V plus minus V source. Okay, so you need to know this relation. You have plus and minus because you need to deduce which sign. Okay, let's look at the first one. Let's look at the first one, the green one here. I will write it probably in green, it will be better. So we have 828. This is what is heard here. It is equal the one which is emitted, which is F, okay, F multiplied by the velocity. The velocity here of sound, which is 343, and here 343, and here I need to decide the detector. Who is the detector? It is the observer here. It is not moving, so I write 0. Okay, plus or minus, it doesn't matter. Okay. Now for VS here, for here for the source is the car. Since the car is moving away, so it tends to increase to decrease the frequency. It will decrease the frequency. Okay, whenever the source is moving away, it decreases. In order to decrease, I need to put here plus V of the car. Why I put plus? Because when I put plus, the term here becomes larger, the denominator is larger. When this one is larger, the fraction becomes smaller. Okay? So I obtained here that the sign should be plus. I deduce it because it's moving away. The frequency, the total frequency here, the new frequency should be smaller. So I need to put plus such that the fraction becomes smaller. From the red here, what I put here in red, it will be like this. So the result is given 971 hertz. The frequency is the same, F, multiplied by the sound is again 343, the velocity of sound. Now, what happens? First of all, the car is moving this way, and the how to call it? The wall is the detector. The wall will be the detector. Okay, the wall is the detector. So here I will put plus or minus 0. The detector is 0. It's not moving. And then 3, 4, 3. So what's happening here? This one will be kind of detected by the wall, and the one which is reflected will have exactly the same frequency. So this one, the sound which is reflected here, will have exactly the same frequency as detected by the wall. Let's say detected by the wall. So we just need to measure here, or to write the expression for what is detected by the wall. So our wall is the detector. The velocity of the detector is 0, and the source is the car. The source is moving towards the detector. Since it is moving towards the detector, we know that the result will be larger. Since it is larger, so I need here to minimize this one. This one is minimum, becomes smaller, the fraction becomes larger, and everything is fine. Okay, great. Now, still, I have this parameter F that I don't know, the frequency which is emitted by the car. It doesn't matter. Why it doesn't matter? Because if I take my expressions here, 1 and 2, I will have 828 over 971. I will do a division term by term. This one over this one is equal to this one over this one. The F will simplify, and I will have 343 over this 343 plus VC over 343. Here I have 343 minus VC, of course, like this. Sorry, my writing was not probably the best one. Okay, now I will simplify this one and this one, and I need to flip this one to the top, and it becomes 343 minus VC over 343 plus VC. Okay, this number here, I can calculate it, or it doesn't matter. I can do the product this way. You have different ways to do that, or I can write it. I don't know which one is the best for you. Okay, just I will write the simplest one. I'm afraid that some will not, some of you will not follow me. Plus VC is equal to 971 multiplied by 343 minus VC. Okay, I can put all the terms which have VC in one side, all the terms without VC in other side, and at the end I can get V of the car, which is equal to 27.26 meters per second. Okay, so here I think all of you know how to solve this. Just develop and then put all the terms with VC in one side, all the constant in one side, and you get this. So,
Doctor,
I
I have a
hope.
question.
Yes.
How do you know which frequency to put in F prime or F?
Yes. Thank you very much. This is the most important in all the chapter. In all the chapter, we have 4 cases. Okay. So imagine the two are moving towards each other, or the two. Okay. So this one are moving each other. This one is moving like this, and one is moving this way, the other is moving this way. This one is moving this way, and the other is moving this way. In the two situations here, we cannot know. Here, we do not know. We do not know here what will be the result, because this one might be larger, this one might be larger, this velocity might be larger. It's we cannot predict. But here, we are sure that the F prime is larger than F, and here we are sure that F prime is smaller than F. What does the rule say? The rule says that if the velocity of D or Vs is going towards the other, so the detector is going towards the source, or the source is going to the detector, that increases the frequency. Okay, if we are going towards, the frequency will be increased. If we are moving away, it will decrease. So what should we do? We need to do it step by step. I will take the detector. I will take here, this term here. I will say, the detector, is it moving to the source? If it is moving to the source, I know that F prime should increase. So to increase F prime, I need to put plus, because when I put plus, this term will become larger, and this one increases. If it is moving away from if the detector is moving away from the source, I will say that, oh, so the frequency, it tends to decrease the frequency, so I need to put minus. So this term will decrease. The same thing here. If the source is moving towards the detector, I know that it should increase. The frequency should increase. Since it should increase, what should I put here to increase it? I need to put minus, because when I have minus, the term here, denominator, becomes smaller, and the fractions becomes larger. This is how you can guess which sign. If you put minus here, should the fraction will increase or decrease? And from there, you will deduce if it is the correct sign or no. The second remark is that when you are reflected from a wall, which is not moving, the wall is not moving, so the reflection maintains the frequency. You have the same frequency. The frequency does not change. Okay, great. So I hope this answers the question. If you have more questions, I will take them later on. So now I should be in problem number 6, I think. Yes, this one. Sorry, it is not loading. Just one moment. What's happening? Yes, great. Okay. So now this is, I think, chapter, chapter 18, if I remember well, or 19 probably. Yeah. So 1/3 of a mole of a monoatomic ideal gas is taken along the path ABC shown in figure 3. How much heat is transferred in the process ABC? First of all, of course, here the number of mole is important. We'll use it as a number, but the keyword here, monoatomic. Monoatomic here is very important. Ideal gas, most of the time we work with ideal gas, but here monoatomic, we'll use it later. It's a keyword, and I will show you how to use it. So you see here what we call the PV diagram. In the PV diagram, be careful about the units. If you have atmosphere, atmosphere is not an international unit. If you have liter, liter is not an international unit. Liter, atmosphere, not international unit. Not an international unit, okay? So here you need to put them in the international unit. In this one, Pascal and meter cube, that's fine. Okay, now how to answer this question? How to answer this question? So we want the heat, which is Q, in the process A, B, C. Let's start by writing what we know. We have the change in the energy is equal to Q minus W. Change in energy, Q minus W. So from here I can write Q is equal to delta E plus W. Of course, if I want ABC, I will put here ABC and here ABC. Okay. Now, for the change in energy, it doesn't depend on the path. The delta E does not depend on the path. So it depends on the initial and the final state. You go this way, you go directly as you wish, you will always get the same thing. And it has a formula which is always valid. It's N CV delta T. It's N CV delta T. Here it's N CV TC minus TA. The final temperature minus the initial temperature. Okay, great. Do we have the temperatures here? We don't have them. We don't have the temperatures here. But there's always a relation that we need not to forget. It's PV equal to nRT, which means the temperature is PV over nR. So here I can write it's N. CV is 3 over 2 R. For monoatomic gas, it's 3 over 2. For diatomic or diatomic gas, it is 5 over 2. For polyatomic, we need to add it's 6 over 2 R. Okay? So be careful. Here we are using this keyword here, monoatomic. We need to use 3 over 2 R. TC is this one. TC, I need to write P C V C over NR minus P A V A. It will give me TA here over NR. As you see, N R simplifies with NR here, and we get it's 3 over 2 multiplied by PC VC minus PA VA. Now we just do reading. The pressure here is 10 to the power 5. It's C. C is the pressure is 10 to the power 5. Yes, that's fine. and the volume is 10 to minus 2. Is 0, 0, 1, which is 10 minus 2, minus for A, it is 2, 10 minus 3, and the pressure is 10 to power 5. Okay, let me up. Sorry, one moment. Oh, one moment. Yes. So from here we get 3 over 2. This will give me 10 minus 3. Or this one is 10 minus 3. So is okay, 10 minus 3 directly minus 2, 10 minus 2. Sorry, 10 to power plus 3, and here 10 plus 2. So it is 1000 minus 200, which is 800. 800 over 2 is 400. 400 multiplied by 3 is 1200. 1200. The unit is joule. So as I said, this one does not depend on the path. So it's NCV. This relation is always valid. Always NCV delta T. Okay. Now for Q, for W, I need W to get this one. W ABC is equal to the area. W depends on the path. Be careful. W depends on the path. So it is equal, since we are moving and the volume is increasing, so it is the area and the curve. If the volume is decreasing, so if we are moving this way, be careful. You need to take minus the area. So the area usually it's either plus or minus, depending on the volume. Is it increasing? Is it an expansion? Or here is it a compression? So it is the area. The area, as you see, you need to take the whole area, not just until here, not this one, not this one. You need to take the whole area. So you need to add also this one. The area is equal to what? We have a triangle and a rectangle. We need to sum them. So summing the two will give us, okay, let me use this color here. So we have the base. The base is equal to what? It's 0, 0, 10 and 0, 0, this one. So it's 0, 0, 8. This is the base multiplied by the height here. The height is from 1, and I have here 3.5, which means 3.5 minus 1, it's 2.5. 10 to the power 5, and over 2. The height, the base multiplied by the height over 2. This gives me the first area plus the rectangle. The rectangle here is 008 multiplied by the height here is 1. And when we do the calculation, at the end here it gives me, I check my notes here, 1800 joule. 1800 joule. Up. Since I have this, Q is equal delta E ABC here, delta E plus ABC. I did not write here ABC as here, just to remind you that it does not depend on the path. So it's 800 or 1200 plus 1800, and this will give me 3000 joule. 3000 joule. I come here up and I say it's this one. It is this one. Okay, great. So never forget that PV equal to nRT. You might write some relations, but this one is always valid for the gas. Then delta E does not depend on the path. It's equal to NCV delta T. You can write it in all the processes. All the processes, you can just write it from the initial and the final. No need to go through B. Don't forget, CV depends on the gas. Monoatomic, it's 3 over 2R. The diatomic is 5 over 2, and polyatomic is 6 over 2R. So be careful.
Can you write
all this information? Yes.
Can you write
Yes. Yes. So you have mono atomic. You have CV, which is equal to 3/2R. Diatomic is here we have 3 translations. Here we have 3 translations plus 2 rotations. And in polyatomic, we have 6. We have 3 rotations and 3 translations. For CP, it's always this one plus R. So it's CV plus R. Here it is CV plus R, and here it is CV plus R all the time. Okay, this is all the time. W does not. W depends on the path. Q depends on the path. Only delta E doesn't depend on the path here. Okay, let's move on.
Doctor, I have a question.
تفضل نعم.
The question said 1/3 of a mole.
Yes.
Does it make any difference?
No, actually the n simplify at the end.
Okay.
So you see here, it's just a number, and you see, oh, how should I use it? But it doesn't depend on the number of mole. Yeah, very good remark. Thank you very much. Okay, now number. Okay, where's the? Oh, I think now I think 7 probably. Yes. Yeah, this one. Okay, so here during a thermal expansion process at constant pressure, 970 joule of heat are added to 1.75 mole of an ideal gas to heat it from 10 degree to 25 degree. The gas does plus 223 joule of the work during the expansion. Calculate gamma. Okay. So be careful. Gamma tells you by definition, gamma is CP over CV. First of all, it's always larger than 1 because CP is always larger than CV. Okay. Gamma, usually we use it when we have an adiabatic process. In an adiabatic process, we have PV gamma is equal to constant. PV gamma is equal to constant. And what does it mean? It's P initial V initial gamma is equal to P final V final gamma. So here where we use gamma. Now, to calculate gamma, we need this one, CP over CV. Here, what they gave us, heat. We have heat. The heat, which is added, Q, is equal to N. For heat, we have 2 formulas. We have N CV delta T. We have NCP delta T. NCP delta T. Here, let me just read it again. And joule of heat are added to 1 mole of an ideal gas to heat it from 0 centigrade. The gas does joule of joule during the expansion. Calculate gamma. Gas heated from.
It is constant pressure.
Yes, yeah, I was searching for this one. Yes, sorry. I was reading just from here, and I was surprised that they don't say that. It's this one, yeah, at a constant pressure. Yeah, thank you. I was searching for this word. So, since it is a constant pressure, okay, so up. I will do some, I will summarize something. Q has 2 formulas, which is NCV delta T or NCP delta T. This one at a constant volume, this one has constant pressure. So we need to use this one because at the constant pressure. Okay, so Q, okay, I will write Q is equal to NCP delta T, and we know the value of Q. It is given here, which is 970 joule. Then the change in energy delta E is equal to NCV delta T. NCV delta T. As I told you previously, NCV delta T works all the time. You notice here, NCV delta T, here NCV delta T. This one is delta E, this one is Q. So this one works all the time for delta E. whereas this one works for Q only at a constant volume. Only at a constant volume for Q. Okay, great. We have this one, and this one is Q minus W. It is Q minus W, and Q is given 970, and W is given also, the gas is doing plus this one. So we need to, the work is 223. From here, we deduce what is the value of 7 of the, what's the value of the change in energy. We obtain this number. Oh, let me do this. Oh. Now, I use this relation. Okay, what's the use of this one? Why did I write this one? Now we will see why. If I write Q over delta E, in this case where Q is equal to NCP delta T, so this one is NCP delta T, and delta E is NCV delta T. This one simplify, this one with this, it's CP over CV, and this one is gamma. You see? So we obtain the gamma just by using Q over delta E. We come here, gamma is then equal to 970 over 747, and this is equal to 1.3. Gamma has no unit, it's a number, okay, it's a number, and it's always larger than 1. And of course, gamma can tell you which gas are you studying. Is it mono? It can. The question can be, is the gas monoatomic, diatomic, or polyatomic? So what will you do whenever they ask you this question? Is it monoatomic, diatomic, or this one? It's either you calculate CP, either you calculate CV, or if you have access to gamma, like here, you have access to gamma, you say that, oh, I have for 3 over 2R, and CP is 5 over 2R for monoatomic. So here, when you do the ratio, you will get gamma is equal to 5 over 3. 5 over 3, if you do this one, I think it is 1.3. So the gas is monoatomic. If you look at the second diatomic, for example, it's 5 over 2R, and this one is 7 over 2R. If you do the ratio, gamma is 7 over 5, and this one is 1.4. So you see, it's this one and not this one. So it is monoatomic. So this is just additional information. But here we just need the number. It's 1.3. We answer this question, and we go to the next one to get additional point. I hope this one is clear.
This is not a adiabatic process, right?
No, this one is a constant pressure process. In an adiabatic process, Q is equal to 0. Q is equal to 0 for adiabatic. If it is adiabatic, you cannot. It's just 0. But for sure, the gamma, you use it when you have an adiabatic process. Okay? You use it when you have an adiabatic process, but you can extract the value by using an additional process where you have a constant pressure like here. But the use, this one, is for adiabatic. I was summarizing here. Here I was just summarizing. But the process which is given is constant pressure, so we use NCP delta T. Okay. Great. I will take the questions, all different questions later on. Now we have this problem here. We came to the entropy. Find the change in entropy of 100 grams of ice at 0 degree. That is isobarically. These words are very important. Isobarically. Okay, which means the constant at the constant pressure. Isobaric. Isochoric is constant volume. Isochoric is constant volume. Isobaric is constant pressure. Heated slowly. So we have a cube of ice. Okay, at 0 degree, it is heated until 100 degree, and here it becomes, of course, water. Okay, so we have this situation. Sorry, one moment. I will plot it again here. This is the cube. Okay, and here we have 0 degree. This is ice. And this is water at 100 degree. Of course, the pressure is the atmospheric pressure, is constant pressure. It is heated slowly to reach. Oh, sorry. Why did I have 100 degrees? It's 80. Sorry, it's 80 degree. It says here. Heated slowly to reach 80 degree Celsius. The heat of fusion of ice is this one. What is find the change in entropy? I want delta S. Okay, so for delta S, if you look at your formula sheet, you have here N CV ln of VF over VI plus N R ln of TF over TI. One of the relations which is valid all the time is this one. But this one works for gases. Be careful. So this it works for gas. You will not use this one. Here we have ice, and then we have liquid. So what is the relation that you have to use? Not this one. The one that you have to use is delta S. First of all, here we need to understand what is happening. We have this one. First of all, we'll have a fission of this one. So we will have water at 0 degree. 0 degree. This is water. So this one, we have a fusion from here to here. It happens at a constant temperature T, which is 0 degree. Delta S, when we have a process like this, we have a fusion, it will be M, L, the latent heat over the temperature T. Temperature T, of course, I write here 0 degree, but in thermodynamics, we need to use Kelvin, ML over T. Should I use plus or minus here? This one is heated, so it's gaining energy. It is gaining energy. Since it is gaining energy, so Q, which is here, ML is the heat, which is Q. Q is positive because the heat is gained by the system. Okay, so this is in the first process, this one, plus to go from here to here, we have MC. Be careful here, it's C, okay, the specific heat, ln TF over TI. So this relation is different from this one. It's different. This one we use it for ice, change of phase, we have a liquid. This is what we need to use. So this one is okay. This relation is okay. We can use it. And as I said here, it's plus, not minus, because it's not. We are heating. So the system is gaining heat. It's positive. So the mass is 100 gram. So we need to use the international unit, right? Do you agree with this? And L is 1 over the temperature is 0 degree. So it's 273 plus. Okay. So you see here, I put 100 gram, which is in gram. I should change it to kilogram because the international unit. But if you notice, CW, which is here, C of water, is given in calorie per gram per Kelvin. So if I let this one in gram, M in gram, and L here per gram, they will simplify. I will be fine. Or I need to change both of them. Here, no need to change because this one is gram. This is over gram. Here, it will simplify. I will let it just like this. But here, the mass. Oh, sorry. Yeah. I'm talking about this one. It's over gram, not kilogram. So I let it in gram. I let it in gram. No problem. It's 80. This is 80. Here, I let it in gram because it's over gram. The same thing here. The mass, I let it in gram because CW is per gram, not per kilogram. Okay, it's not the international unit. It is not the international unit, but it's fine because it will simplify. And then the T final is 80 over 0 plus 273. If we do the calculation, at the end we find 55 calories per kilogram. So this is the change in entropy. It is positive, okay? And we come here, we say this is the answer, and we continue. I hope everything is clear here. We have a change of phase. It happens at constant temperature. The change in phase, we need to use ml over T. If we want the heat, it's ml. This is the heat, ml, and T is this one. And for the change in entropy is this one. I remind you just the heat is ml for the change of phase, and Q. The second is mc delta T. This one, in this, when you go from here, this is the change in heat, mc delta T, but the entropy will give us ln because we need to integrate Q over T. Anyway, this is just some reminding from the lecture. Okay, great. So,
Doctor,
yes?
the formula for the gas is
Yeah, yes.
Is
What's
it
wrong with it?
NR ln VF VI plus NCV ln T
Oh,
final?
probably. Yeah, I might be mistaken. Yes, here it's NR and here NCV. Yes, yes, yes. Yeah, oh, sorry. Yes, absolutely. Yes, absolutely. Yeah, yes. It's NCV, this one. Yeah. I'm sorry about that. Yes. But you have this formula in the formula sheet, I think. Okay.
Yeah, we have it.
Yeah, but you should not use it here. You should not use it here. Okay. Any question? Fine. Everything.
Why we use another S?
Because this one we are working with liquid and solid, so you need to use this one. Here you don't have a gas.
Yes.
But the problem is that students, they just take the formula and they forget what is it used for. We forget with time. We forget what is it used for. So this one is for gas. Okay, so let's come back to the last problem. Last problem here. Where is it? Should be number 9. Where is it? I don't see number 9 here. Yeah, this one. Okay, so this one is about thermal expansion. We have a cube of aluminum, and they say what is the change in density of an aluminum cube of mass 200 grams and of edge length 5 centimeters. So they give us the edge length here, and this one is heated from 10 degree to 80 degree, and they give us the coefficient of linear expansion for aluminum, which is this one. Okay, great. Here I will show you two methods, and I will give you a very, very important hint or tip. So be careful. Here, as a reminder, we have usually when we have a length L, it becomes L prime, and L prime will become L plus delta L. Okay, so we have an expansion, or we say L prime minus L is equal to delta L. Okay, so great. Now we want this delta L. Delta L, how much? Something will increase in length. So delta L is equal to alpha L delta T. So it is proportional to the change in temperature. It's proportional to the initial length, and we have a coefficient alpha. This is the coefficient of linear expansion. Okay, linear expansion. If this one, we can write it again, is delta L over L is equal to alpha delta T. Just keep it in mind, no problem. Now, if you have an area, let's say you have a surface here, and you want to look at the area, delta A, you will see that you have the same relation, but you have 2 alpha, A delta T. If you have a volume, it will be delta V is equal to, we call it beta V delta T, which is, this beta is 3 alpha. So in 1 dimension, 2 dimension, and 3 dimension for volume. Okay. So this is just a reminder. Now, if I take here this quantity and I want to express rho, the density, which is the initial density, rho 1. The density, I will calculate it. They gave me the mass, which is 200 grams, over the volume, which is 5. The edge here is 5 centimeter, 5 to the power 3. I can express it 8 over 5. It's gram per centimeter cube. I write it in gram per centimeter cube. You can change the units, no problem. You can change the units. So this one 8 over 5, which means 16 over 10 is 1.6. The unit is not that important, okay? But here, since they gave me gram per centimeter cube, I left it in gram per centimeter cube because I need to compare. Since they want the change, right? They want the change. So first of all, I need to express the new density. I will recall here the density is the mass over the volume. I'll just put it here if you have forgotten. Rho is equal to m over v. This is what I used here. M over the volume. Okay. Now for the second, it will be 200. This is the mass does not change because of the temperature. And the volume, what is the volume? Is the length cube. And the length is, it was 5 centimeter, but this 5 centimeter will increase by delta L. It will increase by this amount, which is delta L. So I will write like this. So 200 over the new volume, which is 5, plus delta L. As we said, it is L alpha delta T. Okay, 200 over 5 plus the length is 5, and alpha is what is it? 23, 10 to the power minus 6, and delta T is 70 Kelvin or degree. It doesn't matter because it's a difference. Okay, so this should be correct. And here, so you can work this way. You can work this way, but a very important remark that you need to put in mind whenever you work in this chapter for thermal expansion. When you do the math like here, you need to keep all the digits. Keep probably 6 or 7 digits. If you do not do that, I'm sure that you will lose and you not get the correct information. For example, one will say, oh, I will calculate delta L. He will change alpha, L, delta T. He will do the math and he will get here, for example, 0.55. He will say 0.55 is okay, is accurate. I have 2 digits. And he replace here and he will not find the correct result. It will be a little bit far from this one. So here, if you use this way, you arrive until here and you keep all the digits, the result will be fine. The result will be fine. Why I'm saying this? Because as you see, the change in this chapter, all the changes are very small. They are of the order of 10 minus 3, 10 minus 4. Because you see, the coefficient is 10 minus 6. So if you do not keep a lot of decimals, at the end you'll be for sure you will do an error. So rho 2 minus rho 1 in absolute value. This one, you do the calculation, you will find 1.5922, okay, gram per centimeter cube. Here you do this one and you get 7.703 10 minus 3. So you see it's 10 minus 3 gram per centimeter cube. So this is one method. You calculate this, you calculate the new one by taking the new length here, and from that you can deduce. That's correct. Okay, that's all what you need to do the exam. That's what you need to do the exam on this chapter. But sometimes the way you do the calculation can be better. I will show you here. So this one is another method. you have rho, which is m over v. If you have seen in your lecture, or probably have seen this in the lab, you have rho is changing because of the change of v, and m is not changing. I will write it like this, m v exponent minus 1. I would write it like this. So you have something v like this. If you remember in your lab, in 102 lab, you have studied this. Delta rho over rho is equal to delta m over m, but delta m is 0, it does not change, plus this one, delta v over v. And you have, because this one is minus 1, it becomes minus 1 here. You have this relation, delta rho over rho is equal to minus 1 delta v over v. You can see it this way, or let's say it's the derivative of rho, d rho over dv is equal to what? From your from your math, you know that it's m v squared. Okay, but this one is minus m over v, 1 over v. This one is rho. So you can write d rho over rho is equal to, you put dv here, it's minus dv over v. You get the same result by derivative or using the rule you have seen in the lab. Now, what is delta v? You have v is equal to delta L to power 3. The volume is L to power 3. It's kind of derivative. This one is 3 L squared dl, or delta L. Okay, delta L cube, you have seen that also in the lab, it's this one. If you change, delta rho over rho will be minus 3 L squared delta L over L cube, and this will give you minus 3 times delta L over L. So you have rho, you have it, delta L, you calculate it. Okay, this one is minus 3 alpha L delta T over L, the L simplified. So delta rho is equal to minus 3 alpha rho delta T. You can use this relation. Probably it's a little bit sophisticated, and you cannot use it directly because it has a lot of math. But I wanted just to show you how it works. If you use this one, you can get the result directly. Yes. You can use ln. Yes, this one. To obtain it, you can use ln. Actually, this relation, yeah, it comes.
Don't give us
Sorry, I did not. I cannot hear you very well.
if they don't trust the length.
Delta, the length here, it doesn't depend on the length. It depends on rho, just on rho. Because rho, when you calculate the rho, you will need the length, of course, here. That's fine. But as a physicist, you should know this one. As someone who just do like a calculation, that's fine. But as a true physicist, you need to know this relation here. You need to know how to do this one. But in the exam, as I'm saying, you do not know to. You are not required to know this. You are not required. You can just use this one. Okay. You can just use this one. And as I told you, be careful here when you use this one. You need to take. I suggest for you to take 5 or 6 digits. 5 or 6 digits or decimals, because here you have 10 minus 6. You will be sure at the end that the result is correct. When you calculate something, for example, you start by calculating delta L, keep 5 decimals or 6 decimals. Keep them, okay? If you do not do that, you will not get the correct result. You'll be far.
Can I calculate delta V instead of delta L?
Actually, this delta V is this one. This is V. This is V prime. Okay. So when you do this, this is V prime. This is V prime. If you calculate this one is V prime. If you do the difference, you can get delta V. Yes, you can do this that also. But the same thing, you need this. You need to be accurate. You need to be accurate. Here, look. Here, I did not calculate. I did not use L at all. I just need delta T. I just need delta T and the initial row. But yes, you can use any relation. You can stop at any moment. You can just work here. You can just work here. You can work this one. You will get always the same result. But when you do this, you need to be very accurate. Take a lot of decimals. That's it.
Okay, the equation of delta V is 3 alpha V delta T. No need for delta L, right?
Yes. 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 Here you can use 3 alpha V delta T over V. Yes, thank you very much. It's even better. When you use delta V is equal to 3 alpha V delta T, you simplify here, okay? And you get the result directly, this one, without using this one, which might be complicated. Thank you very much. Absolutely, yes. I want to more details, but I don't need this detail here. This step here is not needed. This step is not needed here. You can use directly here. Delta V is 3 alpha V delta T, and you get this result.